our intrepid 15-year-old is now getting really ambitious and has decided to measure wind speed also. All right, to do this, you've gone up to the roof of the house to do it and put in one of these windsocks or something which measures wind. Actually, that you can look online, but there are instruments for doing this that really seem kind of old-fashioned, but what's used. So now you're going to get a three-dimensional vector: temperature, humidity, and wind speed. And again, we'll do this at, say, 3 p.m. in the afternoon, at least the latter two variables. Okay, but it turns out that the cat has chewed up all of your barometers in the backyard, so you do not have measurements of humidity anymore. All you have about humidity is the predictions, right? So you only have measurements of temperature and wind speed, right? But presumably, you know, the whole system is somehow sort of related in some mysterious way, and so the humidity is probably related to the temperature and the wind speed and so on. So it's not like you're looking at sort of variables that are completely independent here. All right, but this does mean that the dimension of our observation space is now different from the dimension of our state space. We'll assume again that x minus xf, these are now three vectors, are normally distributed in the same way. Covariance B is a 3 by 3 matrix, and y, the observations, are distributed now normally again with covariance matrix R, but R is only 2 by 2 and y is a 2 vector. Okay, we might expect again that XA, the analysis state, is the forecast plus some multiple of y0 minus something. Well, that something has to be related to the forecast, so we got to figure out how that's related to the forecast, because that's, you're going to subtract it from y0, so that's got to be a 2 vector, not a 3 vector. Okay, so the question is now, what is the gain matrix going to be? What are the dimensions of it going to be? Well, it's clear that it's going to be multiplying a 2 vector and produce a 3 vector, right? So it's an n by m matrix, right? So it's going to have n rows and m columns, right? So, well, n is going to have to be 3 and m is going to have to be 2. So it is no longer a square matrix. Now Q is going to have to take in a 2 vector and give out a 3 vector, right? So Q is going to be equal to some matrix applied to XF, right? But that matrix H is going to take, right, T, S, and W, right, the 3 vector, and give you just a 2 vector, which is T and W. In other words, it's projection onto the first and third coordinates, right? So that's going to be, see if I get it right, is going to be a let's see, is it a 2 by 3 matrix? It's going to multiply a 3 vector, right? So it's going to have 3 columns and 2 rows, right? So it's a 2 by 3 matrix as opposed to K, which is going to end up being a 3 by 2 matrix. Okay, so how do we derive the gain matrix in this situation? So it's going to be a little bit trickier because of all these sort of dimensions, right? But this is the typical situation because the observation space is never the same, or in any practical situation the same as the state space. So you have to deal with this situation. So all right, so again, these are the specs. X is normally distributed, Y is normally distributed also. So the idea is going to be to use the optimization approach and to try to get out of it an interpolation type formula, right? Like a gain type formula. So we want to find a K so that the interpolation formula holds, so that the XA here minimizes this cost function J of t, right? So notice the cost function is a scalar. Now it's plugging into it an X, right, which is a 3 vector. So the first inner product is in 3 space and the second inner product is in 2 space, right? But both give out a scalar, so that's okay. But you want to plug into this x, you want to plug in a 3 vector. So how does the second inner product depend on x? Well, it depends on x through taking y is equal to hx, right? So x is a 3 vector, but you end up with adding 2 inner products, the first of which is in 3 space and the second in 2-dimensional space. All right, so this is our j of x. Now the question is, what is going to be the formula for the gradient of j sub of j at xa? All right, well, there are going to be 2 terms in this, right? The first term of it is going to be the derivative with respect to x of this x minus xf b inverse, inner product b inverse x minus xf. So we want to just get that first term. Well, it's very useful to figure out what the gradient of xax is, right? And so that is actually 2ax. And that's going to be useful in working this out. So we did this before already, because this really doesn't introduce the dimension stuff. And the answer is that the first term in this is going to be 2b times x minus xf. Okay, so the tricky part is going to be figuring out what the derivative of the second term is with respect to x. Okay, so now we've got this. Remember, y is equal to hx. So if I write it out in matrix notation, then y minus yo, inner product r0 times y minus yo, is hx minus yo, because y is hx, r inverse hx minus yo. And what we'll do is we'll write hx minus yo as the sum of these 4 things, right? So this will actually help us work out the calculation. And it turns out it's going to be quite helpful to have another expression for the gradient of something in this sort of notation, and that is this, that the gradient of where d is just a vector, d transpose times x is equal to d itself, where d and x are the same dimensional vectors. Okay, so you can try to think about that a little bit. What's the gradient of j going to be? You can see there are going to be, if I plug this hx minus y0 in this sort of expression in here into that first thing, right? I'm going to sort of be multiplying various things. It's a quadratic that would in principle be 4 different terms. So let's work out what those are. You can pause for a minute and see if you can think that through and check that out in your mind. Okay, so let's write this complicated expression out, right? So this first thing, I'm just sort of plugging in the expression of hx minus yo, right? This is plus hxf, so I'm adding and subtracting in hxf, right? Minus yo transpose r inverse, and then that same thing, hx minus hxf plus hxf minus yo, right? So now we're gonna think of this as divided, this vector here is divided into 2 pieces, this piece and this piece, right? And then over here we got this piece and this piece, and then we're going to multiply it through, and this will give us sort of 4 different pieces. So this is going to be equal to hx minus hxf transpose r inverse hx minus hxf, right? That's this piece against this piece, and then plus 3 other pieces. Okay, I'll just write those out and then come back. But you can try to think them through too. Okay, so what we're seeing we got here is the first term that I wrote out, but now I've added in these other 2 terms. You might notice that the 2 cross terms are actually the same. They look different, but they're transposes of each other, and they're each scalars, right? Because they're inner products, and the scalar, the transpose of a scalar is just itself. So you can take the transpose and you end up with two of those two things, plus then the second bit times the fourth bit, right? Up there in circled in yellow, right? But notice now that when we take the gradient of that, right? We take the gradient of this. Let me call this J sub O of x, right? When I take the gradient of this J sub O of x, because that's for the observation, it's the observation piece, right? The last term is going to drop out altogether. The first term is going to be just like, well, sorry, it isn't just like it because of the h, but I can take the h here and factor the h out, right? And then actually what I end up with is the derivative is going to be, you can check this, is 2h inverse r inverse h, right, times applied to x minus xf. That's not sort of applying exactly the same thing as I had before, right, with what we had in the previous slide. Now I'm going to use this formula up here because the second term here is really just d transpose applied to x, where you factor out the h and the x is the x minus xf. So this is actually 2 times h transpose r inverse, right, applied to h xf minus yo, right? And the last term differentiates away. So you're left with just the sum of those two terms, okay? Okay, now we put these two things together, right? We want to find what the gradient of j is at x, and we want to set that equal to 0, and then that will be our xa, right? So it's going to be the xa is going to be the thing where the gradient is equal to 0. Well, the gradient of j is the sum of the two terms we found in the two previous things. So let me write those out, and you can try to bring them up and yourselves and see if you've got it right, and then I will come. Okay, so now this is the expression for the gradient of j, and we have to set that equal to 0. All right, so now it's very similar to before. It's just that you've got this sort of all these kind of nasty h's sitting in there. But anyway, you can work it out and get an expression for xa. And let me write that formula out for you. You might try to do it, and then I'll come back. Okay, so I've collected the terms in x on the left-hand side, and I've called it xa because that's xa is the analysis, and that's where the gradient is going to be 0. And then I've collected all of the other terms on the right-hand side, and the form is very similar to before. You know, it's just like the sigma 1 squared over sigma 1 squared plus sigma 2 squared, but now you've got the b inverse instead of 1 over sigma 1 squared, r inverse instead of 1 over sigma 2 squared, and you've got the h's because of this dimension of the observation space being fundamentally different. If you work that out, you see you get this expression for xa is equal to the forecast minus this thing times hxf minus y0. Right, so this is exactly, well, we'll rewrite it as xa is hxf plus, now then this rather horrible looking expression, b inverse plus h transpose r h inverse h transpose r inverse times yo minus hxf, and that's more consistent with the way we wrote things before. So now you see that this guy here is the gain matrix K. So this is exactly the formula for the common gain matrix. So this is the common filter that we've derived by asking what is the minimizer of the appropriate cost function. And now we have a dimension, an observation space that is a different dimension from the original state space. So this is actually works in general, even though we thought about it in the context of our three-dimensional state space and two-dimensional observation space.